Ian has a background in statistical physics, and today he's going to present on text processing and data passing on high-performance computing systems. So without further ado, I'm going to pass the microphone to Ian.
Hi. It's a pleasure to speak with you today. Today I'm going to be talking about data analysis when working with data sets that have very large quantities of text involved. A few caveats about this. First, this is based off my own experience with working on these kinds of problems. So I include a number of references that will explain in additional detail some of the background theory and work that's been done on this by a wide number of groups. But this presentation itself is kind of my own perspective on it, so hopefully that also helps you. I have interwoven throughout it a mixture of slides that are conceptual and introductory with ones that go into a little more detail about how processes would be carried out. So some of them I'm going to skip over and they'll just be in there as notes if you want to come back to this, and some of it will I'll talk through, but if it's something that you're not familiar with or doesn't resonate right away, don't worry. Most of that is not necessary for getting through all of it. We're going to start by introducing the general class of problems that we're going to talk about, and then working through each stage of it successively. So there's a fair amount of material, and hopefully we can get through all of it in today's seminar. So what problems are we actually discussing? The main collection of problems that we're going to be talking about is how you turn unstructured or weakly structured data into clean, highly structured data when you're working with text. This is a multi-stage problem, and there are a lot of moving pieces that work together to make this function. Oftentimes, this will involve merging different data sources. So you'll have, for instance, property tax records and sales records by address, or you'll have products that are being sold on a website and some history of sales, and they'll only be associated through some common text field. And the text fields won't actually be the same. There will be a principle of commonality. They will refer to the same thing. They'll have the same information at some level, but it won't be exactly the same text. If it's exactly the same text, the problem becomes more or less trivial. But if you really want to deal, then it's just a database join, essentially. If you really want to deal with structuring data, you'll find that most historical sources, and even most ones produced now, don't really have regularity in the way that we expect when we're working on computational systems. So it really doesn't lend itself to direct comparison without some intervening model for what the meaningful information is in the text that you're describing. This applies to a very large class of problems, but it is a subset of everything that's in natural language processing, which is a very large field and very old. So we're just focusing in on one piece that has a very natural parallelization, and we're going to discuss some of the details of that parallelization over the course of this. So the overall framework for how we get this done is we start with our input text, and then in the first step, we're going to split it into logical pieces. So we're going to use some parsing principle to break it into multiple chunks, each of which have a well-defined meaning to us. Then each of those chunks need to be cleaned. They need to be standardized. Oftentimes, the same data will have multiple representations. So even when you've broken it into the meaningful blocks and identified what they are, you still need to remove irregularities, unusual punctuation, capitalization, stray symbols at a minimum. If you're dealing with multiple data sources, in order to get structured data in the way that all the relationships are represented, you're going to have to compare those data sources, and that's the meat of this problem. Although splitting and cleaning text in practice will take up most of your time, and we'll see why as we go into this, comparing records is really where we build a model for the text analysis itself. And then once we have that model of measuring information out of the text and comparing it, we need to analyze the quantitative outputs of that. And that becomes a problem of statistics or machine learning, depending on your perspective. So then the output of that, once we have analyzed and classified all these records and their relationships, is a structured data set, something we can query and do science on and do digital humanities work on, whatever you're doing in this case. So that's how we get from partially structured or unstructured text to structured text. And we're going to try and work through each of these steps one at a time over the course of this presentation. This is a slide that just summarizes basically what I said. The example we're going to work through is a pretty literal one. So there are a lot of ways that text can be represented and can be structured and broken down. And we're going to go with one that is like a case that is particularly straightforward. Specifically, you have two tables that have data that has some kind of conceptual overlap, so they can be matched up. And we want to join the data in the two tables together to produce one merged data source that has all of that information in it. And we have to deal with all the variations in text that implies. So the data source we're going to be using is going to be a benchmark for data matching taken from the database group at the University of Leipzig. I have the actual source here. They have a number of other sources that are standards in the field for doing these kinds of comparisons and are useful if you're just getting your feet wet and need to test things out. They're pretty handy. So here's a sample of this. This is bibliographic data. So something that we can all kind of relate to conceptually. Each of them there are unique IDs for each field. There's a title for every record because it refers to an actual bibliographic, like a book or a paper or something. There are a list of authors. There's a venue and a year. So this is the basic structure we're going to be working with throughout this talk. And it is immediately apparent looking at the sample that there's a fair amount of deviation in the data. If you look at the first row under this, we already know that even though it looks structured, it looks like it's neatly CSV structured. You have commas separating fields that are quoted, so it looks like it should be fine. In practice, even the first row has information in it that's questionable. So if we run a simple parsing of this, assuming it's comma separated value structured, we'll get a table that already has fields that have these kind of unusual deviations in them. And looking at these one at a time and how we handle them is going to take up a lot of what we discuss over the course of this. So there are a variety of tools that the deeper you go into analyzing the structure of text, you may end up using. In this, we're going to stick with some of the more standard tools, which are regular expressions and a data structuring tool, working together to do these comparisons. So immediately looking at this, a number of questions arise about what we can do to make this into clean data, what we have to do to make this problem solvable, basically. And answering these questions will lead us to successive changes to the data, transformations that make it cleaner and cleaner. But the cleaning and the splitting is an iterative process. It's something that we'll have to work through interactively to a certain extent. So over the course of this, we're going to be using tools that some of which are more lend themselves to interactive environments, and then build up to applying them in a batch kind of context where you can run them on very large volumes of data. So now that we have a working example, this brings us to why are we doing this on computers? And the answer is basically that even with a small number of comparisons, manually comparing text fields can be tedious. When you do this 1,000 times or 10,000 times, it's a lot to work through, and it takes a lot of time. We only have so much time in our lives, and it tends to be error-prone because it is so tedious. You will miss things that if you created a standardized rule, you wouldn't. So it's best if we can deal with the simple cases in an automated way and split off the other cases, the harder cases, to be addressed by humans as needed. So how hard would it be to do it manually? It comes down to a question of the number of comparisons we have to do. Just looking at this simple case with the benchmark data, we have one file with 2,600 records and one file with 64,000 records. Gives us 167 million comparisons. This is functionally impossible for a human to do by hand. If we were dealing with a larger data source, something with a record for every person in Canada, we would be talking about an incredible amount of data processing that has to be done. In order to make this plausible, we need a strategy that works and it doesn't have any trouble being parallelized. So it has to be a process that lends itself to that, and that's what we're going to aim for as we build up through this. The specific tools we're going to be using will be Pandas for the data structuring work, RE for representing irregular expressions, nltk for doing text comparisons involving metrics and more complicated calculations, and stats models for doing our actual ordinary least squares at the end. Though in that and in scikit-learn, there are a wide variety of tools for handling the statistics part of this. So with all of that said, we're going to jump into the text splitting and cleaning. So the idea behind parsing or splitting up of text into meaningful chunks is that unstructured data is sort of all jumbled together from the perspective of comparing, right? It's single text fields or chained text fields that don't have an innate meaning. When we want to break it down into pieces that are manageable. So this activity of breaking it into manageable chunks is how we're going to do this using a mixture of regular expressions and pandas, and we'll also do that to clean out some of the extraneous characters and noise in the fields. So we're going to start by introducing these in not a tremendous amount of detail. We're going to try and keep this light so that we can get to the more data modeling centric part of this. I like working in Jupyter notebooks, so that's where a lot of these examples you'll see the work has been done in. If you want to use this as a tool, you can access it through syzygy.ca, and there are a number of Compute Canada resources you can use for accessing Jupyter notebooks. So in this case, we need to first get access to the libraries we're going to be using, which the first one is Pandas. The import from and as keywords, if you've worked with Python, we import Pandas and as TD, so we'll be using that to any time we have to call a Pandas function. The first thing we're going to do is what we did manually above, which is pull in the data set as though it were a CSV, because it looks pretty close to one, even though there are some obvious issues with it. And then we're just going to examine it. So looking at the DataFrame name .head will show the first 5 rows, and we can look at the data and get a sense of what's going on in it. Some things immediately stand out about what's gone well and what's gone wrong. The year fields seem to make sense. The IDs seem to be consistent in their structure. These are good signs. We are mostly on the right track. If you look under authors and venue, the very last row, you'll see 2 nams. These are not a number, and for the purposes of Pandas, when you import a blank field, it will be represented this way. This is a special object in Python, and there are a lot of methods for handling blanks in Pandas. And the reason that they show up this way is because it allows us to be more conscious of where something could be about to go wrong. And it allows us to be more explicit in our decision making about how to handle gaps in the data. So the first thing we need to know about data frames, which are basically, to conceptualize them, if you haven't worked with them before, they're essentially like fancy Excel files. It's structured into a table, and you can do a variety of transformations on it, and you can slice it into pieces in a very natural way. So the first thing that is important is splitting off columns, because oftentimes you only want to work with a subset of your data, but you want to work with all of the rows. So this can be done with a command where we pass it a list of columns. Only those columns then will be represented in the output. And if we want to split off a list of rows, we can give a range of rows with the ilope command. And that is exemplified in the input 4 entry there. It shows the second 5 rows. And finally, if we pass just one column rather than a list of columns, we can turn it into a series. And this corresponds to essentially a single column and has some special operations you can do to it. The main work that we are going to be we'll be doing with this, with Pandas, is when we're cleaning and when we're parsing, we're going to split off single columns as series and then use map. Map takes a function as an argument, and it does that function to every entry in the series. So row after row, it will apply that function one at a time. So in this case, what we're doing is we're saying replace the description field with the description field having been turned into lowercase and had white space stripped from the ends. So this gives some sense of the kind of transformations you can do in a very natural way. Like a single line here has cleaned a lot of ambiguity and a lot of variation out of the data that we're dealing with. If we want to add a new column, and this is where we get to actual splitting of the data beyond what's already happened, we can just give our data frame with a new column name in there as the argument. And then we can fill it in with anything that's a column that would match up with those rows. What we'll often want to do is take one of the existing columns and process the data out. So here we took the authors, we filled in all the blanks, and then we used this map function to split the authors into lists of authors on comma. Right? So splitting on comma gave us something that can be compared one author at a time instead of having to worry about the text field. The value of this will become apparent when we start trying to analyze what a match consists of, because very easily you could have two lists of authors that were in different orders but the exact same list. So this successive parsing or splitting of data has a lot of value for understanding, like getting rid of irrelevant variations in the data. The order doesn't matter for them being the same book. It's the same list of authors. So we want to have natural ways of getting rid of that, and this is how we do that. Now that we have some of the basic tools of Pandas in place, we can introduce regular expressions. So regular expressions are a notation for describing text. It's a way of indicating patterns in sequences of symbols. So it tends to end up to be a little abstract, and that abstraction can make it a burden as you get to very complex patterns. But that also allows us to describe find and replace and splitting and cleaning and a variety of other operations that can actually be very hard to do without a way of describing the text patterns to look for as the system processes it. So in this case, the example that we have involves compiling a pattern first of any number of digits, at least one, but any number of them in order. So then when we look through this string, cat123, semicolon, dog456, for any number of sequential digits, we get two outcomes back, the 1, 2, 3 and the 4, 5, 6. This is basically what we're doing. This is what regular expressions is doing. It's specifying a pattern to find and finding all the instances of it. What it does from that point depends on the function you apply it to. So one of the things we can do is we can split on something. We can, for instance, split on a comma with any number of spaces around it, doing stripping of white space at the same time that we split on commas. We can also substitute, and this last example gives us a more complex example of what regular expressions can do. This looks, if you look at in 13, what we're compiling looks for this unusual symbol embedded in the middle of a word. The way this symbol has come about is almost certainly from an encoding error. At some point, someone was running this file through a sequence of different encodings from, whatever, UTF-8, ASCII, or something like this, and a character in another language, in a non-Latin character set. And so it didn't have a mapping to ASCII. And when they did this, they got this percent with an extra 0 or an extra circle on it in the middle of the person's name instead of the actual letter that should have been there. If it were a proper, a standard letter, we would want to keep it so that we could compare it, possibly looking for variations where that something had gone wrong in the other file. In this way. But because it is an error, it's just best to get rid of it. So we're going to look for this character appearing in the middle of a word. And the way we've represented that is by looking for first a word symbol, some letter or number or digit before it, and some letter or number or digit after it, and that symbol in the middle. And when we run it and replace it with nothing, we get the same string back, except that character has been pulled out. So this is the kind of powerful thing you can do with regular expressions, is specify fairly involved patterns and use it to standardize and produce regularity in your data so that comparisons work more naturally. So everything we've done so far is good, but the problem up to this point is that everything is fairly serialized. These would all run on a single Python interpreter on a single node, which is good for testing things out and getting a handle on your data when you're exploring it. But if we want to think about actually making this run on very large data sets, once we've assembled a long chain of cleaning and parsing transformations, in a practical sense, we really do need a way of thinking about this that lends itself to parallelization. And this will also become sort of guide us philosophically when we apply this to comparisons. But this is just parallelizing on a row-by-row transformation basis. So what we're going to base this on is actually a way of thinking about these data sets that comes from Pandas itself, which is the split, apply, combine strategy for thinking about this. In Pandas, this comes about through group by and apply, which are very useful functions and worth taking some time to get to know. But I'm going to outline the idea underneath them, and we'll use that to build a parallelization strategy. So the idea underneath them is that there is something that you can split out subsets by. It could be every row. It could be every row with a year of 2002. It could be multiple columns. However you want to think about breaking apart your data frame, you want to break it into multiple other data frames, and each of those you will apply your complex process to. This gives us a relatively easy way to merge data or do transformations that only apply to small subsets without working on the whole table and doing scans of the whole table over and over and over. That really would wreck the efficiency of it. So instead, we first split it, and then we apply a transformation to each subset independently. And this is the apply part, is that every subset is transformed in some way that only relies on that subset. It doesn't interact with the others. So you can do things that work across rows. In this case, everything with the year 2002 we're concatenating together into one list. This is sort of undoing the kind of thing we just did with splitting out the authors into a list. And then you can merge them back together. And now we've gone from having 5 rows to having 2 rows. This is a kind of aggregation, but in general, you could apply it on a row-by-row basis and just use this splitting concept as an approach to breaking it into manageable chunks. So thinking of this as a parallelization scheme, what we really are doing is we're partitioning off subsets that we want to work on a single node. And each of those can be written to the data set that's going to feed into a job that will run on one node. So this is a very straightforward kind of parallelization. We know that the nodes don't have to communicate because whatever we're doing only operates on that chunk of the data. And in many cases, when you're cleaning and parsing data, it's going to be on a row-by-row basis. So you can use literally any collection of filters that gave you a uniform partition of it to split off the data into chunks and then apply whatever you would have done with the apply function. So in the split apply combine framework, this is the second step. Once you've split it, you would have applied something. Instead of doing this on a single node, that function now becomes a Python script that you will run as your job script. When you run that, it'll do the transformations. It'll all run on that single node as part of that job. And then at the end, we'll recombine them together. Just as happened here, once the transformations were done, we re-merged them into a single table. The difference is now we have to wait for all the jobs to finish. And once they're done, then we can recombine it into a single table by creating a new data frame and reading in the outputs of our separate jobs and concatenating them to that data frame. And you'll end up with a data frame that has had all your cleaning operations done, but they ran in parallel as separate jobs on separate nodes. And this makes life a lot easier. You also, using this approach, you don't have to submit a request for a large number of nodes. You can submit a job array where each job refers to a data subset, and then you just have to pay a serialization cost for recombining them. And I have some additional notes on how you can think about this in what the trade-off really is. I'm going to skip over some of them, but in essence, there is some serialization or serial calculations that have to happen on both sides of this. Splitting it is to a certain extent a serial process, and combining them back together is a serial process. So if we're going to do this, so if we're going to apply this to this case, we really have to think seriously about whether the function we're applying is that complicated. This isn't worth doing if you have if you're just setting letters to lowercase. If you're comparing to a collection of synonyms and trading out words for standardized forms, you may be talking about much more complicated comparisons. And those may be worth doing because applying that in serial could be very time consuming, and you may see a very large benefit that makes it worthwhile. If you haven't worked with this before, Amdahl's law, I have linked to a reference that discusses this a little bit, and you can work through what the trade-off really would be as this scaled. So now that we have, in principle, clean text, so let's assume that we've finished this process of parsing and cleaning, we have to compare it. So what does that amount to? Text comparison is really a way of modeling your data. You're looking at the text and you're identifying what matters and what doesn't, and quantifying that. This is always going to be imperfect and it's always going to have problems, but you want to create functions that say string A is like string B, and it's this far away. The this far away part has to all be normalized to play well together, and we'll come back to that in the last section. But basically you need metrics that express different notions of similarity that are meaningful for your data set. In one data set, commas may be meaningless. In another, they may be everything. And we'll see some examples of this. And this section gets a little bit into the weeds of different string metrics, but hopefully these examples will clear up what I'm talking about. Before we do that, just what computational text comparison is and isn't. The benefits of using this comparison method is that it's repeatable and it's scalable. So you can do this on very large data sets and get the same result every time. The downside is that it's very literal. So if you're used to using close reading methods, this is more analogous to a distant reading method, and it doesn't lend itself to a deep understanding of holistic comparison and contextuality. This is not really what this is for. This is for similarities that are kind of superficial. But it handles them very well, and these are exactly the kinds of things that humans do a terrible job at. It depends on a model. This isn't one of the downsides, I think, of a lot of discussion of machine learning methods, which do apply, many of them do apply to text, is they are made to sound model independent. But in practice, if you're going to get your text comparisons right, you are building a model for what matters in your text. How you build that model, and that's a methodology question, but you are building a model for meaning. And it's going to involve a certain amount of human feedback. There are a lot of so-called unsupervised learning methods for organizing and structuring text. My experiences with them when working at scale on real data sets have been bad. They work to a point, but they don't ever get you to an output that people are actually happy with. You do need humans to address the complex cases and inform what training modifications need to be done and how the method needs to change. So that feedback process is really important, and that will come out as we talk about how we think about real examples. So these comparisons rely on, as I said, a kind of selective similarity. So let's start with looking at two things that, glancing at them, like just looking as a human, you would check a box in an instant saying that these are the same thing. The question is why, and understanding that why is what will drive the design of metrics every time that you make a metric for doing these calculations. So when you look at this, yeah, the title is the same, but that's only part of it. You can have two books with the same title but different authors and be pretty confident that they're different books. In this case, the author comparison is actually a pretty interesting one because we have what is probably the same author name appearing in both, but with an extra letter. Might be a middle name, might be a second first name. It's hard to tell without more context and more like the actual full names, but regardless, there's a good chance that those are actually the same author. And if you have an author matching, having a second author in there is maybe not a big deal. It may not be such a disaster that we have one list with 3 authors and one list with 2. If we had one list with 20 authors and one list with 1, it would be concerning. So quantifying that is going to be an important step in making this comparison quantitative. When we look at the venue, again, there's a comma in one and not in the other, and that's probably not important. It probably provides no real meaningful difference. So we need some way of comparing venue that won't rely on exact matching, that can strip a single character without any harm. So I'm going to work through this. This is where it gets into a little bit into details, but there are 2 examples of distance that I'm going to talk about between strings, and then I'm going to combine them together to make something that does what I just described. So the first one is bag distance, and this works really well when you're talking about lists, and lists that should mostly overlap. So if we can say that D Abadi matches DJ Abadi, and M Cherniak doesn't match DJ Abadi, that will lead us to, in the bag distance, when you use the mathematical definition of that, a distance of 1 between them, which is the smallest distance greater than 0. These are integer distances. So this really lends itself to cases where you'll have order not mattering, where you want to say something that mostly overlap. Similarity in terms of having a lot of the same words in there is good enough. There are situations that's not appropriate for, but in this one it probably is. The second thing we're going to talk about is what we meant in this previous slide by our similar, right? We need some way of measuring for individual strings similarity in a meaningful way. And the example we'll use here is edit distance or Levenshtein distance. This looks at, it was designed for studying typographical errors. So when you have data sets that have randomly mistyped characters, there's a distribution that's been studied for these, and this distance is optimized to capture that. Things that are probably the same because they just had someone mistype a letter or not include something. In this case, DJ Abadi would be almost exactly equal to D Abadi. And this is good in those cases and for things like having a stray comma. Where it introduces problems is with things that will change dramatically on a single letter. Cat is not the same as bat, but the edit distance for cat and bat is still 1, right? The distance is changing a single letter. And so it can't, this distance would not be useful for discerning differences in meaning that hinge on nearby short words. At would also be close to bat. So it's easy to construct examples where edit distance will cause you grief. But it also is very handy if you incorporate it in the right way, on the right kind of data set. So we can use from nltk metrics, we can import the metrics library from nltk. And in that, edit distance is actually an efficient implementation of this. This is actually a pretty difficult thing to calculate if you want to write this on your own. There's a lot that goes into this calculation, so I don't totally recommend trying to recreate this yourself. Bag distance is pretty easy to write your own function for, but edit distance it's a chore. What we're going to do now, and this gives us an example of a real similarity metric. I've used this to good effect. Is the combination of edit distance and bag distance. It doesn't preserve all the nice mathematical properties that they individually have, but it gets us a measure of similarity that is useful. And the way we'll implement it is by calculating the bag distance between these lists. And when we compare individual elements, we'll compare them using edit distance. So as we suggested, the edit distance between DJ Abadi and M. Cherniak turns out to be very large, and it's a lot of transformations you have to do, is the smallest number you can get away with to get between them. So we can split those, we can create a cutoff, and say anything less than 2 is a match, or something similar. And we'll reconstruct the kind of metric that describes similarity among authors, author lists, in the way that we've talked about. But this is actually a pretty substantial number of operations, especially if you're talking like author lists for CERN publications or something like this. If you have hundreds of things being compared to hundreds of things, this becomes non-trivial. There are ways of accelerating it just in and of itself, but we're already, with a very simple metric, we're already at a point where this is not an instantaneous calculation. It takes a little doing. So this process has gotten us to a quantitative description that's useful, but there's a trade-off, and that's the first 2 bullet points on this, which is there's a risk of false positives. If we make our metric too lenient and it ignores important differences, we're going to get a lot of matches that aren't matches, and someone's going to have to deal with that. Similarly, if we make our metric too sensitive to unimportant details, stray punctuation, reorderings, we'll end up in a situation where we're distinguishing things that are that differ in linguistically trivial ways. They don't mean anything, the differences. And so this will actually harm the overall effectiveness of our metric. And so we have to bring those two into balance. One approach to doing that is to use multiple metrics and find some kind of optimal combination of them. This can be done using machine learning methods, and we'll demonstrate this in the last section. If we have a very large number of entities, and this is what we're going to talk about next, that we're comparing, the more complexity we add to get a better trade-off between these two, the more that we will find that we have a real problem with it taking too long to do all of these comparisons. So we need a way of parallelizing this, and we're going to build on the split, apply, combine analogy that we used earlier, only we're going to do something a little bit more subtle this time. We're going to discuss blocking keys. So for forming our groups, the last time when we talked about this, we said we could use pretty much anything to break them into similarly sized chunks to allocate off to nodes to do calculations in parallel. Now we want to take advantage of doing a first rough comparison. We want to actually be able to say that the things that we're going to do these really detailed calculations on are already pretty similar. There's a chance that they're going to match. So we're going to design keys or indexes that can be used to determine what each job, the contents of each job should be in a way that's advantageous. And it will make the most of running those calculations in parallel. But this is only going to work if the key is well designed. So we need a notion of rough similarity. Something that isn't as precise as the metrics we've discussed so far, and can ideally something that can be calculated on a row by row basis rather than on a comparison by comparison basis. So a set of features that have to more or less agree if there's going to be a chance that things will match. And there are a lot of ways of doing this. So key design is a kind of subtle area, but the main things that we want to keep in mind is we want to overestimate. It's okay to have things that are not going to agree in this. We're not trying to recreate the full comparison that we're going to do. We're trying to get a first order overestimate of what the comparisons we're dealing with. And so this is often calculated from a combination of fields. One approach to doing this would be to do it based on things that were published in the same year with the same venue classification, and only compare those. So this gives us an approach that we could calculate from from a single record. Each record individually can have the key calculated for it, and then we can do the key comparison first to build our jobs, and then run the jobs where we do these elaborate comparisons. So to give you a sense of the advantage that this confers, what this does for us, if we did year and publication type, right, and we have these two tables. Here we have very small tables just to demonstrate the effect, and we split them into comparisons that already only agree on year and publication type. If we compared the two tables directly without using this intermediate key comparison, right, we're going to have to do 6 comparisons because every record in the first table has to be compared to every record in the second table. If we first calculate a key and split them off, then we only have to do 2 comparisons, right? The comparison in the first table and the comparison in the second table. And now we're at a point where parallelization kicks in that if we did those in parallel, it would be 1 comparison happening at the same time. This effect grows dramatically as these tables scale up. As their size gets bigger and bigger, the number of prior comparisons would be the number of entries in the first table times the number of entries in the second table. And the number of comparisons that are being done in parallel are the group size times average group size times the average group size. That's much, much smaller. So we can get a huge speed up that easily makes the key construction time well worth it. So as I said, in making a good key, you need to kind of overestimate, and At the same time, you want to keep groups reasonably small relative to the overall data set. If one of your groups takes up half your data set, you're not going to get much out of it. Probably to get something meaningful will take a little bit of design work. There are a lot of strategies for this, and some of my references that I include at the end talk about this, but that, this can be a whole course in indexing and data structure design. So the risks of bad key design really come out in that if you don't overestimate, you can miss matches, right? If your criteria are too strict at the outside and not relevant, you can only be comparing groups that don't include the relevant matches. You can also make your subgroups too big. So again, this is a kind of a tension. If you make your subgroups too big, the processes will run slowly. And it's possible to make key construction so complex that it's actually a burden. But it doesn't scale the same way. So you're pretty much always going to have some advantage here. As I said, if you do these in parallel, you gain even more. So the job construction by key essentially comes down to, once you have your key function, a way of calculating this for every record, it's relatively easy to use Pandas to filter out by key value and write those into data sets by job. And so you'd be applying this to each of the tables, and then the common keys would form the components of a job, and how you would do this, how you would actually run this. Each of the filtered contents of your first database and the filtered contents of your second database would both be inputs for your job. And that job would then compare those two sub-databases. So this is a quick sketch of how you'd go about doing this. To get into more detail, which I'd love to, would take considerably more time. So I'm going to put that up for another situation. But this is the gist of what you would do to make it possible to construct parallel jobs that are only match on key. So what do you gain from all this numeric comparison? Because we're extracting numbers from text that describe the comparisons. And it's obvious on its face that there are 2 or 3 numbers is not going to describe the similarities between texts in a complete way. But if they're well designed, these measurements give a simple comparison of the text, and you can combine them possibly in a way to get errors to cancel. And it's relatively easy to define rules for making decisions. You can say that any match that is where these values, the comparison values, are lower than some distance, which is to say the strings are so close together, they are only one away from each other, then they're a match. That's an easy thing to define. Defining a rule on the original text itself is fairly involved. So numeric comparison is valuable. And if we have enough of these metrics that we build, we can actually resolve the problem of the inadequacy of any individual metric by combining them in some sense optimally. The sense in which they are combined optimally is a kind of subtle thing and depends upon the statistical model you use for combining them. I'm going to describe something that has worked for me a number of times, but it's definitely not good enough for every case. Basically, if you have a series of metrics, and in this, the metrics will correspond to a row of this X table, this X matrix. Each entry in the row, would be the value of a different comparison metric between two entities that you're comparing. So one may be bag distance, another may be some term frequency distance. You would have a whole collection of them that compare different kinds of features and different kinds of overlap. You can find an optimal beta a vector that assembles a single number from them in the most efficient way for applying a cutoff. So when I said a closeness cutoff, with any single metric, it's easy enough to say what a cutoff means. But here you're making basically what is technically called a hyperplane separation. You're identifying basically a split point between the combination of one set of metrics and the combination of another set of metrics. And if you're below that cutoff, then you're close together. And if you're above it, you're not. So this becomes a way of extracting what the optimal way of combining metrics is from standard ordinary least squares calculation. If you have in advance a set of identified matches and non-matches and their corresponding metric calculations. So your rule for making about a decision based off of metrics now can be calculated directly just from having classified some, not necessarily a huge number, more is better, but classified some of them by hand and using ordinary least squares. And then this gives you a way to apply this in the future. You basically, once you have that optimal vector, you can calculate a set of metrics for a new data point, combine them in the optimal way, and compare them to the optimal cutoff that you calculated. And then from that, get a decision about whether they are a good match or not. And based off of, you can do more to determine margins for that cutoff and when it's too close to call or this kind of thing. And this gives you a natural way of splitting your data set of comparisons, your huge number of comparisons, 176 million, into a much smaller number through the parallelization and the key blocking that have a natural cutoff that only a small fraction of them are going to be near that cutoff boundary. And those are the only ones you actually have to look at. The rest are automatically classified to non-matches and matches. So this is, we can spend a fair amount of time talking about the geometry of this and the properties that this kind of approach has. But its main virtue is that it's relatively simple to calculate. Setting aside all the math that is on this page, you're really just using the ordinary least squares function from stat models. And that is a pretty straightforward calculation to do once you have your sample data set that you've checked for being good matches or not. So the main virtue of this is simplicity compared to other kinds of statistical analyses that you can do from the same data to decide what makes for a good match or not. And it has the benefit of not being particularly arbitrary. So, so this covers everything that I expect you to get through today. There are more advanced methods you can use for all of this. You can do richer parsing using using parsing structures from like Lex or Yak or PyParsing, which is very nice. And there you write basically a language specification and can break out your pieces in a very fast and natural way without all these individual quirky functions with regex. There are more advanced comparison measures than the ones we've demonstrated. Term document frequencies are really powerful, and there's an enormous amount of work that's been done on different comparison metrics for different kinds of text data that was done in the context of census deduplication. So there's a long history of this going back to the 20s that different approaches to this problem and some really incredible metrics, but many of them take a fair amount of time to explain. So it's worth digging through this in Christensen's reference. And there are other machine learning methods for approaching this than linear regression. That's just a very manageable one that comes with some nice visualizations once you do it. But there are a lot of approaches you can use, and yeah, would always recommend that you sort of explore some options for that if that's an area that you have enough familiarity with to do that, because it's there's a complicated relationship between how you parse and clean, how you compare metrics, and how you statistically model them, and oftentimes you're juggling trade-offs between them. You can actually get out of all of the doing cluster or doing analysis in advance of manually doing a subset of them by doing an unsupervised learning method. I have had bad experiences with it personally, but in principle, if you can make it work, all the better. And there are dimensionality reduction methods that simplify the problem based off of matrix factorizations of term frequencies. So there's some really neat things out there that you can do to enrich and improve your analyses of these. And hopefully we'll get a chance to talk more about these in other occasions in the future. So these are all references that I love, and I recommend to learn more about this. That's everything.